Hello, and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 1944, number of visible people in a queue. There are n people standing in a queue, and they are numbered from 0 to n-1 in left to right order. You are given an array of heights of distinct integers where heights of I represents the height of the ith person. A person can see another person to their right in the queue if everybody in between is shorter than both of them. More formally, the ith person can see the jth person if I is less than j and the minimum of heights of I, heights of j is greater than the maximum of heights of I plus 1, heights of I plus 2, ... heights of j minus 1. Return an array answer of length n where the answer I is the number of people the ith person can see to their right in the queue. So Leetcode provides us with this quite funny example here with the, I think, minions from that one movie. I forgot what it's called, but these guys were the minions and they talked really weird. Anyway, let's look at an example. So in this one, we can see that the people that the first person can see is going to be, this minion, they can see this minion and this minion. The reason they can't see this one, even though they're taller than them, technically this minion here is blocking their view, so they don't see this one. And we can reference, the formal definition. We can only see this person if everyone between this person and this person is actually shorter than both of them. So that's not the case here, so that's why we can't see this person. But it makes sense, right? This guy is blocking the sight line. So if we were to kind of think about the result array that we expect to return here, let me get my pen back. How do I get my pen? Okay, cool. So the first person, this index 0, sees 3 people. Then this person here, who can they see? Well, they can only see this person to their right. And remember, you're looking to your right. You can't look both directions. So they only see this person because this guy blocks the rest of the queue. So they only see one person here. Then we get to this person here. So they can see the person below them. And they can see this person here. And this minion here is blocked off by this taller one. So that's why we can see 2 people from that index. Whoops. Let me get rid of these markers here and kind of clean this up. So 1, 2. Now we are looking at this person, and all they can see is looking up to this minion here. So they can only see one person. And then this person here, they can only look down and see this one. And obviously there's nothing left here, so they can only see whatever's left in the array, so that one person. And then this last minion person thing, there's nothing for them to see, so it's 0 for them. So that's how we solve the problem, and it seems quite simple when you're looking at the example, but actually pulling this off in code is a little bit more complicated. We're going to want to use a monotonic stack here to solve this question. So before we go to the editor, let's kind of think about how we can derive the approach that we want to use intuitively, and then we're going to code it up. So I left you with a little bit of a cliffhanger there and told you, okay, well, we want to use a monotonic stack, but I didn't really go into detail on how we're actually going to do that. And I don't want to go into too much depth because I think it's much easier to just look at the code than actually me going through an example, because it's quite painful with me trying to draw with my mouse. But essentially what we want to do is we're going to have a monotonic stack, right? So we'll just say that this is S, we'll call it our stack. And what we want to do is we want to go from right to left. And basically, we want to parse out the current height from our heights array here. And we want to, keep track of how many people we can see. And the way that we're going to do that is if the stack is non-empty and our current height is greater than whatever is at the top of the stack, then we want to increment our visible count. And this will just be a variable tracking the number of people visible at a certain index. And it's going to start at 0. And we're going to increment this count by 1 for every person that our current height is greater than in the stack. And we're going to pop from the stack, because remember, monotonic stacks, typically you kind of keep them updated by some sort of condition each time. And our condition is that basically we want to keep track of the highest people. So what we're going to do, let's kind of go through this basic example. So obviously we go from right to left. So we start here, and in the beginning our stack is empty. So there is actually, I'll just kind of get rid of this because it's a little bit difficult to see. We'll just go like this with the stack. So obviously this person you know, they're the first person, so they can't actually see anyone. So we're just going to put their height into it, which we can see is 9, right? Then we get to this person, and what we want to do, and then we want to update our actual result array. So this last person is going to be able to see 0 people, obviously, because there's no one to their right. And then we get to this person, right? And they're of height 11. So we check, does the stack exist? Yes, there is something in here. And is our current height greater than whatever's at the top of the stack? It is. So remember, we increment our visible count by 1. So now it's 1. And then we pop from the stack. So this 9 goes away. Now the stack is no longer valid because it's empty. So that means that we can stop our iteration. And now all we want to do is set our answer for that person to be the count of visible, which is 1, and we want to put their height into the actual array here, into the stack. Then we move on to the next person. So this gets reset to 0 on every iteration. And again, the stack is not empty, and their height is their height is not greater than the other person, which means that essentially we can't pop from the stack at this point, right? Because we only pop from the stack when our current height is actually greater than whatever's at the top of the stack. But because the stack has someone in there, that means that we can at least see the person to our right. So in this case, this person can only see 1, and we move on, and we're going to put this height into the stack. So we're going to put this 11 into the the 5 into the stack. And then, we move on to this minion, and this minion is of height 8. So the stack exists, and, our current height is greater than whatever the top of the stack is. So we can remove this, and we're going to set visible to 1 because, we have seen at least one person. And then we run up to the point where, we can't go any further in terms of popping because 8 is not greater than 11. So we don't pop anymore from the stack. But since there is someone greater than to the left of us, or to the right of us, and we know that because the stack is not empty, we can actually increment our visible by 1, and then we're going to put that into the kind of result array. Then we move to this person. So, and then we also put their height into here. So the stack is going to have 8, and it's going to have 11. So now we get to this person, 6. Their height is not taller than the tallest person in the stack. Or the most recent item in the stack. So that means that we don't pop from the stack, and remember, the visible gets reset to 0. But the stack is not empty, so that means that we see at least one person because we can just look to our right. So that's why this person is going to be 1. And then we set that, and then this gets reset to 0. It's already 0, but that's fine. And then before we go to the next person, their height gets put in. So now the stack is 6, 8, and 11. Then we get to this last person of height 10. So remember that we want to pop from the stack while our current height is actually greater than the top of the stack, and obviously that the stack exists. So we can see one person because we pop this 6, so we increment by 1. We're greater than the 8, so we increment by 1, and now we have 2. And now we get to the 11, but obviously 10 is not greater than 11. But because the stack exists, that means that we can see this person here. So we increment it one more time by 3. And we get, this is our final solution, which is what we had earlier. So that's essentially what we want to do. This question is really simple code-wise. I think it's just more of the difficulty of actually setting up the monotonic stack and the condition that needs to be met. Essentially that our current element, while the stack exists and our current height is greater than whatever's at the top of the stack, we want to pop and also increment the visible count for that iteration. That's what we need to do with the stack. So enough rambling. This has gone on too long. Let's go to the code editor and type this out because it's going to be so much simpler when you actually see the code. So I'll see you there. Okay, we are back in the code editor. It is time to write the code. So what are we going to do? Well, we want to go from right to left through our heights here. And remember that we need a monotonic stack, which is just going to be a regular stack, but we're going to apply some properties to keep it in the order that we want. And we're going to need a result array, which is going to store the number of people visible for each given index of our array. So let us define some variables. So we're going to say that n is going to be the length of height. So basically this is the number of people in our queue. And we want our result to be 0 times n. So we're going to set up our result array. And we're also going to need a stack here. So what we need to do is, remember, we need to go from right to left. So we're going to say for I in range n -1 down to -1, because we want to go from right to left. We're going to say that the current height is going to be heights of I, and the number of people visible is going to be 0. And what we want to do is, while the stack is not empty and the current height is greater than whatever is at the top of the stack, we're going to say, okay, that means that we have one person visible. And remember that we want to keep our stack monotonic, and it's going to be monotonic increasing. So we want our stack, we want to get rid of anything that our current height is greater than. So we're going to be popping from the stack while the stack is non-empty and our current height is greater than whatever is at the top of the stack. So we want it to be increasing, basically, only in the stack. So we're going to do that while one of these conditions is, or while both these conditions hold true. And when it doesn't hold true, then we get out. Now, remember that we can run up against a person in the stack who is actually taller than us, but we still want to count them because we can see them, right? For this person, they can still see this height 11, even though, we don't pop them from the stack and actually count them as a visible person. Basically, what this is going to do is going to count all the people between the next higher person, but we still need to count that higher person if they exist. And they're going to exist because the stack is going to be non-empty when this breaks. So basically, this is the condition that broke here, not the fact that the stack was actually empty. So we're going to say if stack, so basically if there's someone left that we can see, we need to account for them. We're going to say visible plus equals to 1, and then that is going to basically track how many people are visible. And now we just need to say res of I is going to equal to the number of visible people, and we're going to append our current height to the actual stack, and we're going to continue on from right to left. And all we need to do, is just return our result at the end. Let me just make sure I didn't make any syntax errors, and it looks like we're good to go, and we can fire this off. And it works. Excellent. So what is the time and space complexity for our algorithm here? Well, for the time, if you think about it, we are going from right to left through our heights array, right? So because of that, our runtime complexity is going to be big O of n, where n is basically the number of people in our queue. For the space complexity, we're going to have big O of n as well, because the stack here could potentially end up storing all of the heights, and the obviously the result is going to contain n people. If we don't want to count the result, that's fine, but the stack, in the worst case, could end up storing the n people, because it could be the fact that our stack is actually decreasing from right to left, and therefore this condition will never actually be met. Our current height will never be greater than the height before it, so we're actually just going to end up storing everyone in the stack, because we're never going to end up popping anyone. So that's why it's big O of n for the space. So that is how you solve this problem. I think it's a lot more complicated than Leetcode would make it seem. It's a hard question. It's a little bit confusing, but as you can see, it's, what is this, like 20 lines of code, and that includes like function signatures. So it's really not that bad. I'm not sure if this is really a hard question, but that's just my opinion. Anyway, if you enjoyed this video, please leave a like and a comment. It really helps with the YouTube algorithm. If you want to see more content like this, please subscribe to the channel. If you want me to make a particular video, just let me know in the comment section below. I typically make videos that my subscribers ask for, unless it's a dynamic programming question, in which case, sorry, I don't do those. Otherwise, thank you so much for watching, and have a great rest of your day. Bye.